In this lesson, we're going to be talking about the error when using a Taylor series to approximate a function. So here in the blue, I have the graph of sine of x, and what I'm going to do is I'm going to use the Taylor series approximations with higher and higher order. So we see that the first order, it's a straight line, not very good. But as we increase the order, then the fit starts to get better. Here it is at third order, here it is at fifth order. But the point is, no matter how high you get, you can't add an infinite number of terms. So your approximation will always be a little bit off. As you can see, there's this gap. So close to the center, there's not much of a gap. But as you move further and further away, there's a gap between the blue graph and the red graph, or the actual graph and the approximate graph. So the two questions we want to address today, first of all, is what is the value of that gap, or can we estimate what that gap is? And the second question is, how many terms do we need to close that gap to a much smaller number? So, for example, if I go to the seventh order, the gap is nearly gone, and if I go to the ninth order, the gap is practically gone from what we can see. We're going to be looking at two types of series, alternating series and non-alternating series. So we're going to start with alternating series. Here's an alternating series, which is actually just the alternating harmonic, and we can see that as we add more and more terms, that this series, in fact, will converge to some value somewhere in between negative 0.6 and negative 0.8. Okay, so the question we want to ask is, what if we don't add forever? So what if I only add 3 terms? How close am I to the actual value, which was somewhere around here? Okay, well, it's hard to know because we don't know the actual value, but I can tell you that the gap between where we are at right now and the actual value has to be less than the next term. The reason for that is every time you add a term, you actually jump over the value for an alternating series. So you go past it. Here it is after 4 jumps. Here it is after 5 jumps. So every jump takes you further or past the actual value. So I know that the gap from where you are, here you are at the 3rd jump again, so the gap between the 3rd jump and the actual value is going to be less than that next term, which took you way too far. Here's the handout we looked at in class that I'll email to you. So it turns out for an alternating series, the maximum error of the Taylor series has to be less than just the absolute value of the next term, because the next term jumps too far, so the gap is actually less than that. Okay, so let's look at the first problem, which is asking us to use actually the Maclaurin series for natural log of 1 plus x, which you have in that handout or table of common Maclaurin series. The easiest thing to do when you're approaching these kind of problems is actually to write out the series. So it's x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and again, this is all in your chart, plus dot dot dot. In sigma form, it's sigma n equals 0 to infinity, negative 1 to the n, x to the n plus 1 over n plus 1. Okay, so now let's look at question A. It says determine the maximum error if the 3rd order Maclaurin polynomial is used to approximate natural log of 1.2. In order to achieve a natural log of 1.2 in the argument there, we have to let x equal 0.2. So here's the strategy we're going to use. We're going to plug in 0.2 wherever we see an x up to the 3rd order, and then we're going to ask what is the error of that approximation. So natural log of 1.2 is approximately equal to, everywhere I see an x, I'm going to plug in a 0.2. So 0.2 minus 0.2 squared over 2 plus 0.2 cubed over 3, and I stop there because I'm at 3rd order. The question is, what's my error? Well, if you remember, the error for an alternating series has to be less than the next term, which would be sitting right here. So all I know is that my error has to be less than the absolute value of 0.2 to the 4th over 4, whatever that number works out to be. It turns out that it's actually very, very small. If we take a look at what's actually happening graphically, here's natural log of 1 plus x, and if I take it to the 3rd order, here's what it looks like. Now I'm approximating what's happening right around 0.2, so if I kind of zoom in a little bit so I get a closer look at it, you notice if I move my cursor to 0.2, there's hardly any gap, so the approximation is actually pretty good at 0.2, but it turns out if you work out the value we calculated in the worksheet, that it's a little bit less than 1 over 1,000. Part B asks, determine the number of non-zero terms needed to ensure that the maximum error in the approximation of natural log of 1.1 is less than 1 over 10,000. Well, in this situation, we're going to let x equal 0.1. Now, there's two options, both of which are very valid. The first one is the most straightforward. The second one, you have to be careful. One of the things you can do is the same thing we did. Wherever I see an x, plug in a 0.1. But the problem is I don't know how far to go, so I'm just going to write as many terms until it feels like I should stop. So if I plug in 0.1 everywhere, I get 0.1 minus 0.1 squared over 2 plus 0.1 cubed over 3 minus 0.1 to the 4th over 4 plus 0.1 to the 5th over 5. And I feel like that might be enough. What we're looking for is we're looking for the term that's less than 1 over 10,000. And then that's going to be the error term that we can toss out. Well, just kind of calculating each one, this is the first one that becomes less than 1 over 10,000. So what that tells me is I actually don't need this term, and I don't need any of the other terms beyond it because it's going to be negligible in terms of the accuracy. So to answer the question, how many terms are needed? Well, I only needed 3 terms. If I want to know what order, well, you look at the highest power, so we're looking at a third order situation. So that's option 1. Option 2 requires a little bit more algebra. And what we're going to do is we're just going to look at the general term. So you need to be able to write the pattern. The general term for this looks like this. 0.1 to the n all over n. Or if you prefer, n plus 1 all over n plus 1 starting at n equals 0. And I would like to know when this jobby is less than 1 over 10,000. There is no algebraic way to solve this. So here's what we're going to do. We're going to actually plug it in the calculator. What we're going to do in our graphing calculator is plug in 0.1 to the n plus 1, but I don't have an n, so I'm just going to write to the x plus 1 as my variable, over n plus 1, or again, I don't have an n, so I'm just going to write over x plus 1. The easiest place to look at the values and determine what the answer is to look at the table. Okay, so if I look at the table and I'm looking for the first value that is less than 1 over 10,000, I see that it occurs here at n equal to 3. Okay, when n equals 3, I'm within my desired error. So let's go back to what we're talking about here. So the answer here was n equals 3, but when n equals 3, the power here is actually the 4th power. So similarly to the first option, I don't need the 4th power term, so I need up to the 3rd order term, and if you count how many that is, that's still 3 terms. If you turn the page, we're going to move on to question 2, which deals with sine of x. So if you remember, sine of x is just the odd powers, because sine is an odd power, so it's x over x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, plus dot dot dot. If you prefer the sigma form, it's going to be sigma n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. Okay, so either way is fine. In part A, we're asked to determine the number of terms needed to approximate sine of 1 using the Maclaurin series for sine to ensure that the maximum error of the approximation is less than 1 over 1,000. Again, you have two options. Number 1 is just to plug in 1 and look for the term that's less than your desired error. So I'm going to go ahead and plug in 1 wherever I see an x, and I'm just going to search for the first term that is less than 1 over 1,000. It turns out that if you calculate it, this term right here is less than 1 over 1,000. That means I don't need it, and I don't need any of the other terms beyond it. So let's make sure we understand the question. Determine the number of terms. It turns out I need 3 terms. If you were asked what order, you would say that that's a 5th order because the highest power there is 5. If you were an option 2 kind of person, here's the general term right here. You can ignore the negative 1 to the n because it's going to be an absolute value. So plugging in 1 for x, I get 1 to the 2n plus 1, which is just 1, over 2n plus 1 factorial. I want to know when that's less than 1 over 1,000. Again, in this situation, I'm going to turn to my calculator. What we had was 1 over 2n plus 1, but that's just 1, over, and then on the bottom I had 2n plus 1 factorial. Okay, so let's go ahead and look at the table and look for the value that's less than 1 over 1,000. If you look at the value that first occurs, it's going to occur here when n equal to 3. So let's see what that means in terms of the series. So the answer that your calculator would give you is that n equals 3, but you have to be careful, because when n equals 3, that means I'm up here at the 7th power, so I don't need the 7th power. So if you look back at the original sine Maclaurin series, that means you don't need this term, so you need 3 terms. You have to be aware what the series is really saying to make sense of this answer. Okay, so in part B, it says, what is the value of this approximation for sine of 1? So I just need 3 terms, which is 1 over 1 minus 1 over 3 factorial plus 1 over 5 factorial. If you plug that into your calculator, it turns out you'll get the idea that sine of 1 is approximately equal to 0.842. Now students will ask, how do you know how far to round? Well, you round to the thousandths place because your error is to the thousandths place. If you wanted to know how close we actually were, because this 1 over 1,000 is an estimate of how big that gap is, well, you could subtract. So you could say sine of 1 minus 0.842, and it turns out that the actual error is 0.0002, so much smaller than actually our desired error. So the gap is fairly small. And you can see here, if I take the 5th order Maclaurin polynomial for sine, and I want to approximate about x equal 1, which is roughly right here, there's hardly any gap. Even if I zoom in fairly close, you can see that at 1, the gap between the red and the blue is almost invisible in this case. Let's move on to the next question to really get a sense of why we're so worried about error. Question 3 is going to illustrate a very powerful idea in Taylor series. So first thing we need to do is we need to form this function f of x. So how we want to start is we want to start with e, which we know looks like this: 1 plus something squared over 2 factorial plus dot dot dot, which in sigma form looks like this: sigma n equals 0 to infinity something to the n over n factorial. In this particular situation, what we're plugging in is we're going to plug in negative x squared. So e to the negative x squared. So wherever I see an e, wherever I see an x, I'm just going to plug in a negative x squared. So there it is. So let's continue to form this function. Next thing I'm going to do is subtract 1. So if I go minus 1, minus 1, minus 1, what I want us to notice is this negative 1 just cancels out the leading term. So the easiest thing to actually do is just start later, because the first term becomes 0. So I'm just going to start n equals 1 to infinity, and if I simplify that, it becomes negative 1 to the n, x to the 2n over n factorial. Okay, but we're not quite done, because the final step is we still need to divide by x. Okay, well, dividing by x, so dividing this entire thing by x, dividing this entire thing by x, really just subtracts 1 from the power, because it used to be 2 to the n, or to the 2n power. Now it's to the 2n minus 1. So this function turns out to be our f of x. Okay, but we're not done, because what we're actually being asked to do is to take f of x and integrate it with respect to x from 0 to 1. Okay, so if I integrate this from 0 to 1 dx, here's what I will get. Sigma n equals 1 to infinity, negative 1 to the n, x to the 2n over 2n times n factorial from 0 to 1. So let's examine what happens when I plug in the bounds. When I plug in the bounds, if I plug in the 1, then that term just becomes 1 to the 2n, which is just always 1. When I plug in the 0, it's actually 0 to the 2n, which is 0. So plugging in the 0 doesn't really do anything. So our sigma simplifies as sigma n equals 1 to infinity, negative 1 to the n, all over 2n times n factorial. If I write out the first 3 or 4 terms, let's see what it looks like. So when n equals 1, it's a negative number, and I get 2 times 1 factorial. When n equals 2, it's a positive number, and I get 4 times 2 factorial at the bottom. When n equals 3, negative number, and I'll get 6 times 3 factorial. And you can catch the pattern already. You can predict that the next term will look like 1 over 8 times 4 factorial, and you can even go further, 1 over 10 times 5 factorial plus dot dot dot. Now let's look at what the question is asking. I want to approximate this integral to an error less than 1 over 100. So I need to look for the term that is less than 1 over 100. It turns out that this is less than 1 over 100. So I only need 3 terms. If I added these three terms up, I would get negative 0.40. And again, I'm stopping at the hundreds place because my accuracy is 1 over 100. Take a look at the original problem. How would you have integrated this in the past? Well, it turns out this integral is very complex, and there's no guarantee that we even have the techniques to be able to do the integral. So what we would have had to turn to is we would have had to turn to the calculator. Okay, so what I've set up here is I've set up the equation that we're going to integrate. I'm just going to go ahead and graph it, and it's nothing remarkable. The magic button on our graphing calculator, again, is second trace, which will give us the calc menu, and we can ask the calculator to integrate. The lower limit is 0, so we hit 0, enter. The upper limit is 1, so we'll hit 1, enter. And you can see that the area under that curve, or the integral, is negative 0.39. Our approximation was negative 0.40, which is within 1/100th of the actual value. So it's remarkable that we encountered an integral that we couldn't do by hand easily, and we were able to find an approximate value by just adding 3 fractions. So the next problem is going to ask you to do the same thing, and if you remember, the power series for arctan of x was sigma n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1, all over 2n plus 1. But in this particular case, if I divide by x, I'm actually losing the power, so this is just going to be to the 2n. What the problem is asking us to do is integrate this from 0 to 1, dx, 0 to 1, dx. And the integral is fairly straightforward. When you integrate this, this becomes sigma n equals 0 to infinity, negative 1 to the n. The new power is now x to the 2n plus 1. And then there was already a 2n plus 1 on the bottom, so it's going to be 2n plus 1 squared from 0 to 1. Plugging in the 0 doesn't do anything, so what all we're really doing is just plugging in the 1, which again doesn't really do anything except for make that a 1. So if you write it out, here's what it's going to look like. And you want to look for the term that is less than 1 over 50. Well, easily here. This term is less than 1 over 50, so I actually only need 4 terms, and if you add that up, you'll see that that approximation for that integral is pretty good.